So basically that's the digital box, right? You use it for the homework. So now you can see the real one. Basically it has a hat, there's a RGBD camera. You can get RGBD images, and the base has LiDAR. You can do navigation with LiDAR. And this arm can be used for manipulation. So now it's charging. So let's unplug it. And then
is it on? Yeah.
Yeah, we can first use the PS4 controller.
Yeah, it's like a controller too.
So, yeah, how about you?
Wait, not controller's not on.
It's not on? Okay.
You can drive it to the area, right?
Yeah.
That is facing the table. So we'll first use some grasping of the objects.
Yeah, I'll just put it back so that it can go into the position easily.
Right. So then you can leap to the torso.
Yeah.
So you can see. Because I'll first do the detection, right?
Yeah.
And you can also control the head, right? That is facing here. We'll first talk about some perception. That's more computer vision. So I'm teaching computer vision next semester. If you're interested in. So then you can come this side. I'll show some demo here. So right now we connect to the robot by Wi-Fi. This is the router. The computer connect to the router, and the robots connect to the Wi-Fi from the router. So what I'll first do is I start RVs. Right. You have used RVs. So now you can see we can get the RGB image and the depth image from that camera on the head. So please come. Here are the 3D points, right? The 3D points from the robots. So now what I'm trying to run is some first object detection. We try to detect the cracker box and the master bottle on the table. I'll first run this. It's a neural network. I take an image inputs and then do pixel-wise segmentation. So you get the segmentation masks. And from the segmentation, you can see here. Basically, this network is trained for 20 objects. 2 of them are the cracker box and the master bottle. That's why you see some false alarm on the back. So how to solve this is just move the camera down. So you don't see much of this. Okay. But it's fine. Let's focus on the 2 objects here, right? So you can see this color means the segmentation masks, and there's the bounding box from the network, and this is running to tell like what's the object detected. But to just know the bounding box is not enough for grasping, right? We need to know the 60 pose. Then there's another method that can estimate the 60 pose of the objects. I'm running it. Okay, now you can see this one, right? This is for these 2 objects, we have 3D models. So we can, once we estimate the pose, we can render this image and overlay with the original image. So this one is the overlaid image with the original image. If you see it's overlaid correctly, that means the pose is good. Also in 3D, right? We have this RGB colored axis. You saw this in homework. But now we have 2 axes that indicate the pose of the object. That means, okay, the 2 objects are correctly estimated with the pose. So yeah, how about you just move the object around? Let's see. You should focus on here. How the pose estimation work. It's a particle filter based approach, so it's trying to do tracking, and we can also move it dramatically, something like that. By the way, you have questions you can ask. Right? So this is a perception side. We call this model based because we need to have 3D model of the objects. So now we have this 60 pose, right? And then Nina will show how can we do grasp planning and the motion planning to grasp the objects. Okay, I'll hand over to you.
I'll just keep one object.
Just interrupt us and talk about if you have questions.
So basically, like for grasping, right, you need the pose. Otherwise, if you don't have the pose, whatever grasp you have planned, it will be incorrect, because let's say, like there's some grasping algorithm, right? It's assuming you have access to the object model, and then it's trying to simulate some grasp, right? So it's assuming that the bottle is like that in this environment. But if the bottle is turned upside down or something like this, that's why you need the pose, because then it will know that you have to approach it from this direction, not like this direction. So once you have the pose, what we'll do is, like, I'll just remove, because the grasping algorithm does not work in clutter. So I'll just keep a single object, and I'm already having access to the pose information that algorithm is running. Right?
Right, we just use those, right? So this computer runs a network to estimate the pose, don't publish a topic. Then the other computer can receive this topic and do some motion.
So first I'll just run the motion planning. So it's like a move it script to initialize the motion planning, right? Because whatever grasp that I generate, it should also find a feasible plan to it, like, because there's a table obstacle here and there might be other obstacles as well. So it will try to generate the feasible plan to it. So by plan I mean, like, with grasp, right, I only know that the gripper should be like this. That's all I know. But how to actually move the arm to that position, that's what move it does for us. And I'll open the IRVL. So that's how it looks like right now, right? That's the object, and that's the look. So what we do is, right, before even attempting to grasp, we try to have that arm in it's called a stow position, which is like a salute. I'll show you. So I have a script here that runs this stowing code. And if I don't have the move it motion planning on, right, it will not even work, because it will have no way to actually move the arm. So the move it motion planning is very critical. I'll show you here, like trajectory. Yeah. So that's like the green thing, the green box you're seeing. That's the robot is treating that as an obstacle, so it should not touch it. And we are like a bit conservative, like we're adding the box in front of the table. So, yeah. So this is now in IRVL. We are visualizing the trajectory. If you see this part. So just to make sure that it doesn't hit the table before actually executing it in the real world. So I can see that it's not hitting the green table at all. So I can like safely execute it. And like you can see in IRVL like how it's happening in the real world. So this is called like the stow position, like before you actually execute a grasp. Because it's easy, right? Like you can execute it from above. That should be fine, right, Jason? This distance.
Honestly, yeah, or you can back up a bit.
Okay.
So we didn't combine navigation and manipulation. Otherwise, it's gonna automatically. So now we use a controller.
So basically, how this grasping is done is, right, in a simulator I've already generated many grasps with this object model, and now I'm just trying to execute any one of them which is feasible on this, like whatever it has observed. Even for this grasp, it will first show the trajectory here and then.
So like each object has 100 predefined grasps. Now the robot is trying to plan to each of them and see which one is feasible. But we first sort the grasp according to the distance to the gripper. Right?
Yeah. So as you can see, right, like if you look in closely, like the yellow part is the observed thing, and the green thing that you're actually seeing, the green shape of the bottle, that's the object model that has been loaded, and that's coming from the pose. So if I rotate the object, the green object will also rotate, and the robot will know, okay, like where to actually grasp it. And so once it has found the plan, it's actually, I'm visualizing the trajectory now. about how it will actually execute it. So once it looks fine in RVS, you can just press it, and it will try to. It's not always robust, but yeah, I don't know what will happen. Hopefully it will not.
So it's moving a little bit slowly for safety.
Yeah. So this is called like the standoff distance, right? It's like you have some tolerance for like distance to the object, and then once you know it's in the correct position, you can just execute it. You go and try to grab it, and then it always asks like whether to lift it or not.
And you can lift it.
You cannot handle slippery.
Yeah. Now.
That sounds research area like a touch sensing, right? You have touch sensor can feel how much force you should apply or things like that. So
Yeah. Even the grasp modeling, right? It doesn't take into account the friction on the surface of the object. So that's why it's. We can show with this object as well, right?
yeah.
Let's try this. Bit different pose. So if you see, like, I don't know, all of you can see, like, I'm just passing in an object ID. So like the 006 was this object, 003 is that object. So both the pose estimation code and the grasping code, they have been trained on the same set of objects. That's like one of the research challenges, like how do you generalize to other unseen objects, right?
Oh, okay.
So again, you see again, like even if the object like was rotated, the green thing, that's the mesh of the object, is being loaded correctly because we have like the correct pose from the pose estimation, and that's the trajectory. Yeah. Deformable objects are not like our specialty.
Okay, I think that's all the
Grasping part, yeah.
So basically this is called a model-based approach. I have 3D model object, we do 6 object pose estimation. Then we use the model for cross-planning and motion planning. Another approach is model free, right? There's some reinforcement learning based. That's we didn't shoot here, but some previous work you can check that. But this demo more about model based approach for grasping.
So yeah, I just wanted to show like here, right? You can see this is the 3D model of the object that I have. This is the mustard bottle and for the cracker box. So using these, we actually plan the grasps. And this actual like 3D file is what loaded in the RX that you see.
So we will target the robots and then Gagan will shoot some navigation.
When I start the demo, I'll talk about how the navigation stack on this robot works, how we do the motion planning, how the robot moves, and how it knows where it is in space in this room. And then we'll talk about how we can explore an unknown environment. Let's say a robot was put into a hall that it doesn't know where it is, right? How does it begin to even understand where it is in that environment? And how does it map out that environment for future use cases? And so that's what I'll be doing then. Okay, so before we get started, just want to quickly introduce. So this robot has a few sensors. So this is the vision image sensor that you guys saw. And there's also a LiDAR sensor underneath here. And so this is a 180-degree LiDAR sensor, and it constantly revolutes, and it knows the LiDAR points from every object that it hits within a certain 50-meter radius or so. And so with that, we can create a map of sorts And based on that, we can do some computation to basically understand where we are. And I'll show that when we get there. So that LiDAR sensor will be used heavily. And additionally, we can also incorporate the use of the depth sensor for items that are higher up in the ground, right? Let's say the LiDAR sensor catches those legs, but it doesn't know there's a table here. The depth sensor can know that there's a table here with that information, right? So we fuse the sensor readings to get a better understanding of the environment, generally. But let me get started. So I'll open up the IRVL here. Hopefully everyone can see. So you can see here that the red dots are just the LiDAR points. And as people move around, you can see that certain points are changing. These are the LiDAR points that the LiDAR scanner is getting, right? So with this information, how can we build out an understanding of which space is empty and free to navigate in, or which space is an obstacle where we can't navigate in, right? That is the question starting off. And so the way we do this is, let me start up a ROS node quickly. Okay, so you can see now that we have these red dots, right? These are the laser scanners, right? But we want, feel free to come in closer if you are not able to see the screen. But we have these, which are the red scans. These are the laser scanners. But what we also did is I ran a ROS node where it computes based on this laser scan which space is free that we know of and which space is not free, right? So for example, because the laser scanner hit here, we know for a fact that there's no obstruction from that robot location all the way to that wall, right? And so I've marked these grids as white, which means they are free and free to navigate it. But you can see that this is an obstacle, aka the wall somewhere, and so we cannot navigate there, and so those have been marked with black, which indicate that they're obstacles, right? We cannot navigate in that location. And so with this information, we can give that piece of information to path planning nodes, and these path planning nodes can take this information to generate a trajectory to some given point in space in order to move the robot wheels in order to get to that location, right? So let's try doing that, for example. And you can also see these color objects here, and they just mean that there's a lot of obstacles in front, and it doesn't want to go there, so we have expanded the radius of that to say stay away from that area. So instead of saying don't go close to the wall, we say don't go even close to a certain radius from that wall, right? So we don't even want to get close to that wall.
So you want higher tolerance, right?
Right.
Okay.
Exactly. Yeah. So we get to that stage. So let me show you how the navigation works. So I'll go ahead and put some point for navigation.
Do you need to create some empty space over there?
Yeah, if you can just give it a bit of space, that's fine. Yeah, it'll be fine, I think. Just in case I have this. Oh, that was the wrong one. Okay, so I'm going to give it a navigation goal. Okay, you can see that it's trying to achieve that goal. All right, let me do math. You can see that it's trying to go towards that goal, and as it moves towards the goal, see how the map is being filled out more, right? So when it turns to a different location, the map gets filled out more. That's the essence of navigation. We want to explore, look at different areas that we haven't seen before, and when we look at areas we haven't seen before, we get more information about what is the environment. And so if I wanted to go forward, I provide a nav goal that just says go forward here, and then the robot will create a plan to navigate to that area without colliding with the objects, right? And if it cannot reach an area, it will tell us that I cannot reach the area, and it will give up. It won't collide into the object instead, right? There's certain cases where it will, but we won't get into that for now. Okay, so is any questions on the navigation aspect, how the robot knows where it is in space, and how it can go to a different location? Anything I might be missing? No? Explain? Okay.
I have a question.
Yeah.
Doesn't it just try to run over the blue area?
Oh yeah, that's a good call out. So it looks like it is, right? But it is going to stay away. So the real obstacles are the pink, right?
Oh.
And so this is a good question. Even though you see it looks like the robot has overrun this red-blue area, this red-blue area is just a guidance. It's a guidance of how close you are to the obstacle, right? So if you think of this as a cost map, if you get closer to the walls, the cost of navigating closer to the walls is higher, right? And so when we plan a trajectory, we want to minimize that cost, right? So we minimize the cost to go to a certain point. And so certain times in this case, we don't have a choice but to take a high cost area. right? And so in this case, we do decide to go in this high-cost area, but otherwise we would try to stay in the center of a hallway because that would be the minimal cost if you imagine it as a 3D grid of sorts. But yeah, okay. So hopefully that makes sense. Any other questions before I move on? Okay, cool. So let's move on. So how do we explore areas in this space, given this information? How do we explore areas in this space that we don't know anything about, right? How do we further build out this map in this room and figure out more information about where this room edges is and everything like that? Because if you look at this map, we don't know what is here. We don't know what is here. We don't know what is here. These are incomplete. LiDAR doesn't know as of now, right? And so in order to do that, what we run something called frontier exploration. And what frontier exploration does, essentially, is it looks at the missing spaces, the edges between the known areas, and the unknown areas, right? For example, in this case, there's an edge here. You can see the white is a known area, but this gray is an unknown area. And so this would be a frontier to check out, to explore, right? And so by exploring an unknown area, you build the map further and further. But you won't consider this wall as a frontier because we know there's a wall there. We don't care what's there or not, right? And so let me run a frontier exploration. I won't move the robot. I'll disable the hardware. But I'll run frontier exploration so you can see what the robot will see in terms of frontiers. So let me just quickly run that. Hopefully everything works. Okay, cool. So you can see all these green dots on the screen here. You can see this is a frontier. This entire edge is a frontier. It's a known area, but it's edging to an unknown area, so it's a frontier. There's a frontier here, frontier here. All these are frontiers that the robot wants to explore. And remember that navigation stack I talked about earlier? Well, now we know that these are frontiers. We can just pick this point as a next navigation goal, and we can just have the robot go that area. And remember that when the robot is facing that direction, the LiDAR scanner can see if that is an empty, open space, closed space, things like that, right? And so if I turn the robot, I can't turn it on manually, but what would happen is the algorithm would pick these frontiers, and we would try to navigate towards each one of them. And as we navigate towards each one of them, we might discover more frontiers. Like if there's a hallway there, and we are going towards the hallway, you might see there's more hallways, and you might find, oh, there's even more frontiers to explore. So it can keep growing until we keep running that algorithm until there's no more frontiers to explore, right? Until we have no more frontiers, and the entire map is filled out. And at the end, I ran this for around 3 hours in this floor, and I had like all the hallways mapped out, all the rooms mapped out, and we can use that information in the future for grasping or for recovery and things like that, right? So that's how you can explore an unseen area. So let's do a quick demo. I guess we can pull it outside in the hall, and you can just see it autonomously explore. Oh, bad idea. That was about to move. Okay. Okay, 1 second. Someone hold the door open? So let me just launch the navigation. Oh, navigation stack. So it has now started scanning all your legs. Say hi. And then I'm going to start the exploration. Hopefully everything is fine. Okay. We haven't run it with this many people here before, so not fully sure what's going to happen. Okay, so you can see it's fully exploring. I'm not controlling it. It's decided that you guys seem interesting, so it's going to go check you out. Yeah. So it's going to go to a certain location, and then it's going to do a 360 turn, so the LiDAR can get all the points it can get, right? So it's doing that turn. It's finding out if there's any more frontiers to explore, and then it's going to decide on the next frontier, and it's going to start exploring that next area. You can see, oh, it finds that, it's going to go to the next frontier, and it's going to keep going. And off it goes. And it's going to keep doing this until someone stops it, or until it's ran out of those green boxes, frontiers to explore, right? Man, it's slow right now, but that's because we made it safe for now. All right, hopefully it doesn't lose Wi-Fi and go rogue, but that's fine. All right, but yeah, it's going to keep going. It's going to explore all the hallways.